Okay, good afternoon, everyone. Let's get started with the lecture today. Just as a reminder, we were talking last time about well testing and hydraulic fractures, okay? And today we'll continue talking about hydraulic fractures for well testing, and then probably we'll start talking about hydraulic fractures for completion. Okay, just to do a very quick review of what we saw last week or on Monday, is the first thing that we saw was about hydraulic fractures in nature, and we say that these kind of hydraulic fractures can already exist in the subsurface. Then we talked about the leak-off test and what is a typical signature of a leak, and depending on where, either if the fluid goes just into the wellbore or it goes into the wellbore and into the fracture, and what happens when it closes. Okay, so we put a lot of time on this, and it is very important. We'll see that towards the end of the lecture, we talk about the homework related to this problem, so I'll get back to this. A very similar signature of the leak-off test is the one also of the DFIT test. But as we were saying, the DFIT test is not done when you're drilling. It's done for completion purposes, for measuring what is the minimum principal stress, what is the fracturing pressure that you're going to need when you are fracturing, and also sometimes to measure also permeability of the formation. All right, so the one thing that I missed here was just to say that this type of DFIT test can be done through perforations, so opposite to the leak-off test that is usually done with a open hole. In this case, for example, if we had a horizontal wellbore and we already had a casing, cemented casing in the wellbore, if we have perforations that go through the wellbore and into the rock, then you can run this DFIT test also through perforations. Some other times also you can do it when you are in the stage of drilling or in a vertical wellbore. But in this case, you are going to be also able to do it through the perforations, and basically just have to isolate the wellbore, place some packers, and then you can run this test as well. And the signature is very similar to the one of the leak-off test, in which, as a function of time, and again, if you have a given injection rate, sometimes you will increase that injection rate, keep it constant for some time, and then stop. Very similar to the leak-off test, you're going to see a pressure that first is more or less constant because you're not injecting, increases, goes to a maximum value, and then decreases. It goes into more or less constant value, and lastly, when you shut in the wellbore, pressure decays and goes and it starts to go down. In unconventional, the difference now is going to be that because the permeability is very low, the method that we applied before is not going to work that well. And in order to analyze a little bit better what could be the fracture closure pressure and what is going to be the permeability of the reservoir, there are some other methods that are used for calculating this pressure. And one of them is called the G function method, in which you use equations for fluid flow in order to explain what is the, let me find it, what is going to be the response of the wellbore and the response of the fracture and how pressure is going to go down. So here you can see an example of the schematic I was showing before. We have injection rate, time on the x-axis, pressure. You can see the response of this wellbore is quite linear. It gets to the breakdown pressure, and then it goes quickly down. It goes into a more or less constant fracture propagation pressure, and then after shut-in, it starts to go down. And after this point, after the shut-in point, that's when you start to analyze the data as a function of time. And the plot on the right is that response that I'm not going to tell you exactly how this works, but I just want you to know that it exists, that using this G function method is similar to the square root of time method, but a little bit more complex. But with that, you are able now to calculate also what is going to be the fracture closure pressure and what is going to be the permeability of the formation. And there are some companies that use this method, and some others that use other methods. Actually, now for unconventionals, there is some debate about this one is true or not. But just the take-home message here is that there are some more advanced methods for unconventionals for the DFIT test that if you're going to work in topics related to this, you're very likely are going to use. And there are some software packages also that allow you to use this as well. Yes, Mr. Morreale. Sorry, say again?
Do you get all your data, like analysis, after closure?
Well, no, you will have all the data all the time. But for this analysis, you just analyze the data after shut-in. After shut-in, that's when you start to analyze your data. And at some point after shut-in, you're going to have your fracture closure pressure. And depending on the method that you use, you're going to be able now to pick up what that fracture closure pressure is going to be. For example, in this method, it depends on the derivative of the pressure decay signature. Okay, let me come back to the dot camera. So here, just remember that one option to get to know what is a fracture closure pressure is going to be the G function method. All right, these two tests, again, they are very similar. Signature is very similar. You go over breakdown pressure, propagation pressure, and closure pressure. And they are done in order to know what is the breakdown pressure, especially in the case of leak-off test. In the case of the DFIT test, what is the fracture propagation pressure and the minimum principal stress. And they involve a hydraulic fracture. And in some of these tests, especially in DFIT tests, you actually want to do a hydraulic fracture. The next test that we're going to see is a test which is actually performed to avoid a hydraulic fracture. And it's called the step rate test. In the step rate test, the objective is to find the maximum injection pressure without fracturing the wellbore. And also when you find the maximum injection pressure, usually that will be related to a maximum injection rate. We have many problems of petroleum engineering in which we have to inject constantly a fluid. And can anybody tell me an example about when we want to inject constantly a fluid? Water flooding, right? Water flooding could be a case. Do you want to fracture a wellbore when you're doing water flooding? Probably not, because otherwise the displacement of oil, for example, is not going to be that efficient. Well, we're going to see an example later where I'm going to challenge that idea. But in general, no, you don't want to fracture a wellbore when you're doing water flooding. Another example could be, well, no, here, this is not for drilling. This is now mostly for reservoir engineering. So we have done the drilling. We have our wellbore. Now we just want to, for example, enhance oil recovery, or we also may want to get rid of some fluids. For example, water disposal. Water disposal from production water or from backflow water. We most times, unless we treat it, we cannot dispose it on surface. So one solution is to dispose it underground. And usually, if you work for a water disposal company, your objective is to dispose as much water as possible and as quickly as possible. So some of these wellbores, they are injecting 24/7. And as I was telling you, this could be production water from EOR. It could be also backflow water from hydraulic fracturing. And there are some other fluids that we could also inject in order to enhance oil recovery. For example, carbon dioxide. You could inject gas like a nitrogen. You could inject a polymer. And you could also inject steam. And all of these are cases in which we face a problem of continuous injection. And generally, when we're doing this continuous injection, we're not doing it in a tight formation. It's usually done in a permeable formation where you can dispose your fluids more or less quickly. And one more thing about this is that this test is very important because there are some regulatory agencies that they also require this test when you qualify for your well to be an injector. So when you apply for a permit of an injector well, some regulatory agencies, they ask you to run this test in order to see what is the maximum injection pressure. What would be an easy calculation of your maximum injection pressure? The easiest number that you should be able to tell me right now. To what pressure you don't want to go above? The fracture gradient. And how do we get the fracture gradient? It will be the minimum principal stress, right? So you don't want to go above the minimum principal stress. But if you run this test, you can actually check what is that maximum injection pressure and verify that you do not fracture the formation. Okay, so let's see how this test is done. The name is tells you more or less what the procedure is. We're going to inject with a rate that increases in steps. Usually, in this test, you more or less predict what is going to be your maximum injection rate that you're going to be using, and then you divide that in more or less 6 to 7 steps. And let's see, how many do I have? 1, 2, 3, 4, 5. Let's do one more. 6. And you ramp up injection, and that's what you set, and then you measure what is the pressure in the wellbore. And this is more or less what is going to happen. At the beginning, we're going to assume the pressure is a constant value. It's not changing because we're not injecting anything. That's a 0 value. As soon as you start injecting, what do you think is going to happen with pressure? It's going to increase, right? And it's going to increase, but opposite to the case before in which we were either injecting a drilling mud, which forms a mud cake, or we were injecting it to a tide formation, now we're injecting into a permeable formation. So we are just imposing a rate in a wellbore in a permeable formation. So the pressure is going, but eventually it's going to level off to the steady state condition. Each time you increase the rate, this pressure is going to increase more or less the same magnitude. If you remember the equation of the wellbore, the rate is proportional to the gradient of pressure or to the difference between the far field and the wellbore pressure. So let's do one more over here. Up to this point, the increases of pressure are going to be more or less linearly related to the increase in injection rate. So if I were to make another plot with pressure as a function of injection rate, what you would observe is that each time you increase your injection rate, say 1, 2, 3, your pressure increases and it's more or less aligned on the same trend. At this point, the wellbore which, let's assume just for simplicity now, it's an open hole completion, is going to be permeating fluid in all directions with a more or less a radial flow, just with the radial flow characteristics. Okay, well, there's going to be a point in which if your injection rate is too high and the viscous forces that injection rate applies on the wall of the wellbore, they are too high that they decrease enough what is the hoop stress that the wellbore is going to fracture. And when that happens and the wellbore fractures, let me draw it over here. What do you think is going to happen with the pressure increase when you increase the rate? Now if it fractures, the fluid is going to be also getting out from the fracture into the rock, and fluid is also going to go through the fracture. So let me repeat my question. We make the same increase of injection rate, would the pressure increase the same as before or not? It will not, because now it's a lot easier for the same injection rate to be injected into the formation. So the additional increase of pressure is going to be a lot smaller than before. And the result of that is going to be that after that critical injection rate, your increase of pressure are going to be less than before. And out of this plot, what we can do is you can trace a line that joins the points in which presumably there was no fracture, and the points for which presumably there was a fracture. An intersection of those two lines is going to yield what is the fracture injection rate. Let me just put it in acronyms. So here we're going to have fracture, let's call it, it's actually called fracture propagation rate. And this one, the same, is going to be the fracture propagation pressure. So let me spell it over here. This is a rate, and this is fracture propagation pressure. Some other times, this propagation is also called a parting pressure or a parting rate. But it means the same thing. It means the pressure at which a fracture is going to start. So eventually now, after you do this test, you report these two values, and these will be now your maximum pressure and maximum rate at which you want to inject in a case like this. So let me show you an example that I have here in my notes. And here you have a little bit more of details about how this method works. And, oh, very important, I didn't write this, but what is the difference in this equation when you have a fracture and when you do not have a fracture? Where would that go in the equation? In S, which is the skin factor, right? So this is telling us, again, that rate is related to pressure, but when you have a fracture, you're going to have a skin factor, and that for the same increase in rate, the increase in pressure is going to be a lot smaller. Okay, so here you have an actual example of injection rate and pressure for a field in Santa Barbara County, if I remember correctly, where you can see very well that in this case, as injection rate increases, as you may expect, pressure increases. It's linearly related because of this equation. And after a certain point, if you keep on increasing the pressure, or the rate in this case, the pressure doesn't go up a lot more. And that's a point at which you have a fracture. Okay. So let's come back to the case of EOR. And let's make an example in which we are in normal faulting conditions. Let me try to do this 3D to see if I get it. Okay, we're interested in displacing oil from a formation that went to primary recovery, and I'm going to say that the minimum principal stress goes in that direction, the maximum horizontal stress goes in this direction, and again, I repeat, this is normal faulting. I'm going to give you two options here. The first one is going to be you put the wellbore somewhere over here, and you push the oil and recover it somewhere over here. This is going to be option number one. Or you put a wellbore somewhere over here, and you push the oil and to recover it in this one. So injector, producer, and this is option number one. A very common problem that you have when you are doing EOR and especially when you're doing water flooding, let's say this is a water flooding example, is that your water is not perfectly clean. There are some particles in it, and also the temperature might be a lot lower than the one of the reservoir. And those two things, the presence of particles in the water and cold water, they are going to favor hydraulic fractures. Why? The first one, small particles, they get clogged into the pores of rock, and it acts similar as a filter cake, elevating the pressure and the gradient between the pressure in the fracture or the pressure in the wellbore and the pressure in the rock. And cold water has the effect of shrinking the rock and lowering the horizontal stress and making that fracture gradient lower. So in both cases, you're going to have hydraulic fractures very often. All right, so assuming that now, very likely you're going to have hydraulic fractures. Which case you think it's better, number 1 or number 2? I'll let you think, and I will receive opinions, and I will give back extra points to whoever answers the question correctly. Yes, Mr. Patel. Number 1, why? It should be what? Okay, can you tell me what would be, say that this is north, east, and this goes down. What? North, south, right? That would be the strike of that fracture. So I hope you guys can all see that a fracture in this case would open as a plane perpendicular to here, perpendicular to the direction of the board. And it looks like in the screen, I don't see that well this line, so let me draw a little bit with thicker lines. Yes, your fracture will be something like this if it eventually forms, coming out from the page. And in this case, if you had a fracture growing out of this injector, let's call it injector number 2, it will start here and it will grow like in this direction. And it will potentially reach, it's going to grow in the other direction too. It will potentially reach the producer very quickly, and then whatever you inject in order to displace soil is just going to break through very quickly through the producer, and then you're not going to displace anything. So in case number 1, just to make it a little bit clearer, if you look from the top, if this is your injector and this is your producer, then what we're going to have is a fracture that opens like this, and when you have a displacement front, it will go into the producer like that, actually displacing some oil, opposite to the other case in which it's going to break through very quickly. Just for the sake of completeness, let's do that one too. Injector, producer. Now the fracture goes straight into the producer. And this is the east, this is the north. And in this case, this is a hydraulic fracture. Okay, so in this case, you can see that a fracture may not be that bad. So just to complete this topic, then, Mr. Cosby, you go first.
So you had case one. Did you actually want to fracture the well, or is that just
The producer,
no, the injector?
the injector, you could in this case. Actually, you could also fracture the producer. That will give you a more efficient displacement pattern and probably higher injection rates and producing rates. But just to make a point here, we're assuming that this fracture, that we know very well what is the state of stress. We're assuming that the fracture is going to grow more or less planar. In practice, that might not be exactly the case. Okay, so just to close with this topic about the step rate test. The step rate test, as we explained, it consists on increasing injection rates, but it has a disadvantage of that it doesn't consider particles in the water. It doesn't consider if then later you pump with colder water. It usually also meant for large reservoirs. In small reservoirs, sometimes the pressure could go up as you start accumulating more fluid in the pore space, and you could form a fracture at a pressure lower than the parting pressure indicated in the step rate test. So you should be also aware of that there are some limitations with the step rate test. Okay, so with this step rate test, we finished the first part of hydraulic fracturing, and for the homework, you have 4 problems that you have to solve, and they're not complicated, and they're due on Friday, okay? I want to do this before you go to the break, so you have to do nothing during Thanksgiving. You can go shopping, you can go enjoy with your family, and and you don't have to do any geomechanics. All right, so let's see. This is going to be, if I remember correctly, homework number 10. I'm going to walk you through the problems. Number 1 is about a leak-off test. Here you have the data from the leak-off test, and here you have the conditions real leak-off test was done. All right. The first thing I want you to do is to interpret the figure and to read the figure in order to get to know what were the conditions at this place. And the first thing to do is to calculate what is the total vertical stress. So I hope that you see the same as I do from the figure. We see a case which is offshore. I read from there that there is a water depth of 2,862 feet. And I also read that the leak-off test was conducted at more or less 8,050 feet of true vertical depth. So here goes the wellbore, and we are interested into a condition which is at 8,000 feet of true vertical depth. So the first part of the assignment is to calculate SV. And you know how to do that, right? So I don't have to tell you now how to do that, but you know how to do it, and you can tell me what that value is. Also, in this case, we know that, let me see. Okay, I'm telling you what the pore pressure is. So if you know the pore pressure and you know the total stress, you can calculate also what is going to be the vertical effective stress. The second part of the problem is to calculate what is the minimum principal stress. As we have seen with the leak-off test, the point at which the fracture closes is going to give you what is the minimum principal stress. We still don't know what is the stress regime in this place. So this is kind of like a reversed engineering of what you see in the results to try to figure out what are the original conditions. All right, here I'm telling you what is a fracture closure pressure, and it was at that time. And from here, you have to use the data that you see in the plot in order to tell what is the minimum principal stress. So as we assumed before, the minimum principal stress, S3, is going to be given by the fracture closure pressure. But there is something here that you have to notice, that you have two readings. You have downhole pressure and surface pressure. And that's something that you have to know very well, and then that you have to be aware of later when you solve any problem, because there is a huge difference between those two. The downhole pressure is going to be measured in downhole conditions. The surface pressure is going to be measured on surface. What is the difference between those two? Any suggestion before I forget to give extra points to Mr. Patel? Yes, there is going to be friction in it, but what would be the most important component? The hydrostatic column of the fluid that goes from surface to downhole conditions. If you're running a leak-off test, then you're going to have a hydrostatic column of drilling mud. If you're running a DFIT test, you're going to have a hydraulic column of fracturing fluid. If you're doing water flooding, you're going to have a hydraulic column of water. So that's going to be the main difference between those two. So from here, you can check what those numbers are, and there is also going to be friction and some other things that are going to make these values slightly different. But from this problem, take the downhole pressure reading and tell me what is the minimum principal stress. So after you do this, you can ask yourself, is minimum principal stress equal or larger or the same than the vertical total stress? And that will allow you to tell if this is reverse faulting or normal faulting or strike slip. And based on that, I'm going to give you a hint. The case is that this is not reversed, okay? So S3 is going to be equal to SH mean. And once you have SH mean, you're going to be able, if you know what is the pore pressure, because I'm telling you that, you're going to be able to calculate sigma H mean. And once you have sigma H mean and you have sigma V, what I'm asking you is to calculate the ratio of sigma V to sigma H mean. and to tell me if this is close to failure or not, and what is also the stress regime. So here the question is going to be close to fault reactivation, stress regime. You can answer that based on what you get over here. Just as a quick reminder, what is the typical value of effective stress ratio when the faults are close to reactivation? It's about 3, right? So if this value gets close to 3, that means that that's going to be the maximum ratio of stress and anisotropy. And in this case, if this is about 3, that would mean that very likely this is normal faulting. Okay, one more thing that you can do out of this problem is that by comparing what is downhole pressure reading and the surface pressure, you can tell what is the density of the mud. So in this case, I'm going to tell you to assume that there is no friction, no nothing, and the difference between downhole pressure reading, let me do it down here because I'm not going to have a space. So downhole pressure is going to be equal to surface pressure plus the density of the pressure of the column of fluid. So that's going to be the density. I'm going to just put here in general fluid. In your case, this is drilling mud for this problem, G, and the true vertical depth between the surface and the downhole condition. And this equation is going to be the same for other cases. Okay, any question about this problem? No? Let's go to number 2 then. For problem number 2, what you have to do is you have to download this file and you have to plot what is pressure and injection rate as a function of time. So let's see if I can do this quickly. Okay. So you guys know how to do this. Appears space now is the limiting character, and let's see what we have here. We have time, pressure, and rate. Okay, so time, pressure, and rate. So I'm going to make a plot of these two. And this is what we get. In order to see these ones a little bit better, something you can do is you can put one of these in a secondary axis. So let's put here pressure in a secondary axis. There you go. And let's change this one to 60. Apparently that's the beginning. And let's change this one to, let's see, this injection rate. We'll leave it like that for now. Okay. So here you have rate and pressure, similar to what we have seen before in the DFIT test. This is actually DFIT test. The injection rate is ramped up, and it's held in a value which is more or less constant, which in this case is about 33 barrels per minute. And this is the reading of pressure. Opposite to what we saw before, in this case, it appears that this goes directly into a fracture propagation pressure. Does not go over a hump. And sometimes, as we discussed, that depends on the in situ conditions and the anisotropy of stresses. More anisotropy will favor an early pressure in order to go into fracturing. And out of this data, what I want you to do is that you find out what is the fracturing propagation pressure, which in this case is about 2,150 psi or so, the shutting pressure, and later the fracture closure pressure. And for the fracture closure pressure, what you're going to have to do is to analyze the data as a function of the square root of time, and you're going to get something very similar. So this is a nicer version of what we just saw. You're going to have something similar to this at the point in which the signature changes from a linear trend to something which is not linear. That's going to be the fracturing closure pressure. Something very important to notice over here is that these readings in number 2 are going to be in terms of surface pressure. So that means that if you want to know the actual minimum principal stress in downhole conditions, you need to add the column of fracturing fluid in order to tell me what is the minimum principal stress. So I'm just going to write it so you remember. You're going to have to add that value in order to get, again, that minimum principal stress. This is sometimes a little bit misleading because the fracture closure pressure may be measured in surface pressure conditions, and we say that's a value of minimum principal stress, but it is a value of minimum principal stress in absolute terms when you add the hydrostatic column. If you don't do that, it's not the minimum principal stress. For example, in this case, probably this is a wellbore at several thousand feet of depth. Minimum principal stress, there is no way that it's 700 psi. It has to be a value a lot larger. So you need to add that hydrostatic column. Okay, the other problems are pretty easy. The third problem is you have the data and you have to interpret there what's going on. For example, how many barrels were pumped? Again, what is the fracture propagation pressure? What is more or less the instantaneous shutting pressure? Something very important out of here is that I want you to learn how to read these plots. We learn the mechanics of it, but also you have to learn how to read them, how to get useful data out of here. And last, just 30 more seconds. What you have to do is interpret a step rate test where here you have all the data as a function of time for each injection step. And once you plot all of this, you're going to get something very similar to what I show in one of the examples. Okay? So, all right, that's it for today, guys. I'll see you on Wednesday.